neurologist and a men's health specialist. And this is our first STEMinar series, and we are representing the S today. And I have a dear friend, Kumar Naryanan, Dr. Kumar Naryanan. He goes by Kumar, is a neurologist who specializes in Parkinson's disease. Kumar, thank you so much for being here with us today.
Thank you so much for having me. It's really fun to do this virtually.
Yeah, you have a lot of books on your bookshelf. So before we get into the meat of the conversation here, talking about the work that you do, can you pull off your bookshelf your favorite, maybe personal book of yours and your favorite educational book for the people watching?
Sure. So my favorite medical book is this one, Localization in Clinical Neurology. So neurology, for those of you who don't know, it's a science of the brain, but it's actually a lot like real estate, because real estate, the most important thing is location, location, location. And our brain is obsessively organized down to the synapse, down to those little, nanometer connections between, individual neurons. And because of that organization, location really matters. So as neurologists, we obsess on trying to figure out where, the basis for movement, language, consciousness, free will. We obsess over questions like that. So I love this book because it goes through everything that's known about localization. And then this is Light in August by William Faulkner. And, William Faulkner's a complex author, but I just love his command of language in the human heart, which doesn't localize well, despite the cardiologists.
Now, you have a 6-year-old and an 11-year-old daughter. What books are they reading right now?
So it's a bit of a problem because my 6-year-old is just learning to read, but she's reading these like huge books. Understands like every third word, and then my 11-year-old is a famous book addict, so she will read anything. In fact, she's read basically every book in the house at least 4 or 5 times. I'm looking because my mom just sent me a whole bunch of books that I read when I was a kid, like science fiction books, Isaac Asimov from like the 1980s. And these books are a little bit of a problem because they kind of reflect the 80s. But she's going to read those. But she would prefer to read anything by Percy Jackson, Brandon Mall, Chris Colfer, any sort of fantasy science fiction kind of book. So.
Yeah. And I know books are kind of a thing of the past, but perhaps our challenge to the students watching are to maybe turn off the Netflix a little bit, grab a book, and maybe choose some of the books that you held up to the screen. So, Kumar, talk to me about the people who influenced you to pursue a career in science early on in your life. Who are the ones who influenced your career decision?
So, it's hard to think about your decisions because they're kind of highly, constrained by your own personal experience. For me, my dad was a scientist. He's a professor at the University of Washington. He studies bone collagen regrowth. He's a biochemist. But when I was young, he would frequently have to do experiments on Saturdays. So we would spend Saturdays in the lab doing. So in those days, there was computers were not very common, so you could go there and use them. Use the computers. I used to play video games or paint. But I was just fascinated by all of the lab equipment around. So that was a key because I was just comfortable in the lab. But then as I became more and more aware scientifically, I was actually really bad at the type of lab work that he did, which is biochemistry. It's stuff in solutions. And the problem is you would add like all kinds of things to the solution, but there would be no indication that anything was happening. And so I would frequently get bored or wash the wrong fraction down the sink. So huge problem. So, but it wasn't until I got the ability to represent the data that you were studying with computer that I started to see that you could actually make these comparisons quantitatively, like mathematically. And then it became really exciting. So the first scientific experience that I had any success with was brain imaging. So we would do fMRI, looking at brain activity, and then single neuron recording. And then I had incredible scientific mentors, specifically a woman, Pat Goldman-Rakish, who was about 5'3". She was a very famous neurophysiologist, but she was such a clear thinker. And I met her. I went to Yale actually as to do my graduate training, to work with her, and she ended up passing away. She was hit by a car while I was in grad school. It was awful, but everything I'm doing is like 5 conversations I've had with Paco Rikic, so it's rotating. So she was an incredibly influential scientific mentor. And then there were, both the University of Washington, where my dad was, and in graduate school, I met all these people who were physician scientists who had medical practices, but they all, had labs. So I thought that was normal. And so for me, those people really made it clear that you could combine asking important questions with stuff that mattered to people. So a lot of us do that, in science, but I think that they were always thinking about, well, how is what I'm doing in the lab going to affect someone someday? So my dad's advisor was a man named Roy Page, who's a very famous periodontist. And he studied inflammation and how that affects, when you go to the dentist and your gums are inflamed, that's inflammation. And so he really made it clear that you could, you do periodontal practice, and then he would, go to the lab and work with my dad. But he made it clear that there's a close relationship actually between science and medicine. They aren't two different things.
Yeah, so Kumar, you are the epitome of a physician scientist, and you have 2 doctoral degrees, right? A medical degree or an MD, as well as your PhD. So it seems like getting both of those degrees was something that was ingrained from a very early on period of your childhood. So why did you decide to pursue both? And do you need to pursue both to asking the questions that you're asking?
So, it's funny. So often, you think about the reasons you just did what you did, and I'm not sure I could clearly articulate it. But I think the thing is, when I was deciding what I wanted to do with my life, it's as if you were departing on a journey, and I didn't want to go on these 2 parts of that journey. So medical school and PhD training are very different in the sense that, medical school is a bunch of hoops you jump through. You have to learn to think exactly like everyone else in some ways. But with the PhD, actually, you're rewarded for thinking like nobody else. You're rewarded for thinking completely, differently and coming up with new ideas. But, along any life journey, you kind of want to enjoy the view, and both of them go through incredibly interesting topics. For medicine, it's kind of like, seeing all of these amazing human experiences and human kind of, human disease, all of which are way more impressive talking to someone who's lived through any experience of that disease. Even if it's a small disease or big disease, it changes their life in very clear ways that resonate with your own experiences. But in a PhD, you sort of take one of those experiences and you kind of delve into this very specific problem at a level that hopefully is, unique and new and that no one else has experienced. But the thing is that the federal government and our societies recognize that combining these training programs has a specific advantage. So I was fortunate enough to join one of these federally funded MSTP programs, which is phenomenal because it really, juxtaposes the medical problems with the ability to delve deep in these problems. And so that experience was just, enormously, first of all, it's really fun. And that's the key part of it. Most people think, well, you get an MD and you get a PhD, and then when do you start your life? But for me, it was, well, boy, do I enjoy these journeys. How do I keep this type of thing going throughout the rest of a career? And so, your career, I don't view my career as starting when I became an assistant professor or when, I view it as starting when you started to ask those questions. But the questions are, I think, the most important thing. I think anybody could ask, all of us have these questions, like, why do you get dementia? What happens when you get dementia? Why do you get Parkinson's disease? Those questions are what's important. And I think one thing that I'm learning, and it's actually really awesome at the University of Iowa, is it's a really diverse, multidisciplinary, collaborative team, and that, the important questions, let's say, why do you get dementia? People with expertise that you might not originally appreciate can have something to say about that question. And so you learn that, answering these questions, it's going to take all kinds of, the questions are really hard and really complicated. And it's going to take all kinds of ways of answering them to make progress. And I think that's what makes science fun, is because you don't often see where an answer comes from.
Yeah. Kumar, you allude to the importance of a team effort. And you have your own lab, and I do want to put the URL for your lab up here. You have a really great pictures on your lab website, as well as some good information and articles attached. So you run this lab, the Naryanan lab. Talk to me about the other people in your lab that allows this work to occur.
So I love talking about my lab because those people are unbelievable. It's unbelievably fun, but they're also such good people who have a real passion and zeal for science. So although you refer to me as direct, I don't, I think of it more like a coach, so we have a bunch of people who are looking to ask these questions. And my job is to try to coach them towards which questions you might be able to answer and which ones won't. So let's say if I pick my favorite wide receiver, Steve Largent, which he's in mid-1980s Seahawks, not very famous out there, or Jerry Rice, Randy Moss, sure, they want to run a 40 in, 3.2 seconds, and they want to be able to, but a good coach is going to say, hey, listen, you're not going to do that, but you can do this, or to recognize their skills and to help motivate them. And there are going to be times when they think they can do things successfully. There are going to be times when they can't. And so, the same role of coach is someone who sort of figures out what person's goal is and try to help them get on the way. So everyone in my lab hopefully has their own goals. So I have people who are fellows, so people who are trained as neurologists, who are movement disorders doctors, who want to start their own lab and answer questions about, say, acetylcholine and dementia. I have people in my lab who are postdoctoral fellows. So these are people who have PhDs who are looking for really focused research experience to help launch their own research directions. I have staff scientists who their goal is just to do science. So my job is to try to protect them as much as possible so that they can ask the scientific question that's most important to them and give them all the resources they need to do that. We have graduate students, and so they're learning how to ask these questions in a sustained way. We have undergraduate students. I have a couple of research technicians, so their goal in the lab is to learn science, to get an experience and exposure to patients and scientific thinking so that they can go into medical school or graduate school. So it's a really diverse environment, but actually those are huge advantages because, as I said, we have people who are trained in biology, pharmacology, clinical neurology, and we're all attacking a problem from many different angles, and that's it makes for a you got to think creatively because again the problems are really hard. The problem that my lab is focused on is why do Parkinson's patients have trouble thinking? So that's all my lab is focused on. That's a really hard problem, and it's a problem that most of the field has failed at for 30 or 40 years. So we have to sort of think broadly and think creatively, think out of the box to come up with ways to make traction on these difficult problems.
I love that. So in many ways, your role on the team is to ask the hard questions. So I'm going to call you Coach Kumar from now on.
Yeah.
Now, you trained at various big name institutions like Stanford and Yale. What brought you to the University of Iowa on faculty?
So, my training was a little bit serendipitous. Like I went to Stanford. Well, I'm not sure if it was serendipitous. I felt like I'm from the West Coast, so Stanford has a lot of purchase over there. But the University of Iowa is really a unique place in the sense that it's really collaborative. People work together. You can get things done. There are not a lot of barriers, and I find that the University of Iowa compares very favorably to many of these more let's say famous East Coast institutions, because the East Coast institutions or the West Coast institutions, a lot of them are just bigger, right? So and there are advantages to being big. So let's say you're at one of these institutions, you're going to find somebody doing everything. But there are also disadvantages to being big because the bigger your institution is, the more the pecking order is, and if someone's doing exactly what you want, you can't necessarily approach them in the same way. But here, at the University of Iowa, where it's much more collaborative, meaning that people are much more willing to work together, much more willing to entertain your question, no matter kind of who or where you're coming from, because first of all, we're not as big and the barriers are lower. And the second thing is a little more subtle. So my wife's a philosopher here at the university, and it's really hard to have a reasonable work-life balance in New York City. Or so let's say Harvard Medical School, there's like 7 campuses, there's like 2 or 3 hospitals, 4 hospitals. You got to take a bus from the hospital to the labs. At Stanford Medical School, is like there's like I think it's a 4 or 5 miles between the main hospital campus and some of the daycares and places you want to live. It's impossible to have a house. University of Washington, the medical school, it's a huge medical institution. The hospital's like, there's a Swedish hospital where all the clinical stuff is 45 minutes away by a bus ride is where the main medical campus is. So it's really hard to make, your work life work together. But in University of Iowa, there's, it's Iowa City. So it's really easy. Like daycare is like, very close. School's 7 or 8 minute bike ride from my lab, which is like a 2-minute bike ride from my house. So it's really easy to combine your work and life and make everything work fluidly. And so those are some of the reasons why. But the last thing is more subtle. Like, the hospital, as I said, is a 5 or 6 minute walk from my lab. So I can see clinic patient and be back in my lab in 6 minutes. If the patient, can't make it or is going to be late, I can run back to lab and see what's going on, come back to the hospital. And so that the size really makes that type of physician-scientist interaction unique. And if you look at it, actually, the University of Iowa has way more physician scientists per capita because of this proximity.
And I couldn't agree with you more in terms of the collaborative environment here. I mean, the first time that you and I met was over coffee, and within 30 seconds, I was like, wow, Kumar is the real deal. And not that I'm like the best judge of character, but it just, you can tell your passion within 10 seconds of you talking about the work that you do. And, we had met to talk about how you and I could help take care of our mutual patients with Parkinson's from both a men's health perspective and the neurologic perspective. So what excites you about the research that you perform in your lab?
So, I'm enormously excited because, we study one narrow problem, but it comments on a much bigger problem. So I'm interested specifically in how we think. And what does that mean? Well, how do we perform these mental operations like math, reasoning, flexibility? How do you remember things for a short period of time? And so that really comes from Pat, who's interested in these things. In undergraduate, when I was doing these brain imaging studies, there's a part of the brain, the front of the brain, this is localized to the front of the brain, called the prefrontal cortex, that lit up every time someone did a complex cognitive operation. But it wasn't until residency when I met my first Parkinson's patient who could not remember anything. In fact, they were using Post-it notes to get through their day. And it brought me back to the very first patient I took care of this is a medical student. I saw this patient in a clinic that we run so medical students can get exposure to patients. The patient had Parkinson's disease, but she had profound thought disorders. So she would go A, B, Z, or she could not make sense. If you gave her medication instructions, she would interpolate a lot of things that you didn't say. And yeah, she had Parkinson's disease, and yes, we can control motor symptoms, but her thoughts were completely disorganized. And if you know anything about Parkinson's, it involves the neurotransmitter dopamine, which has a profound impact on brain circuits. And you can think about patients with ADHD or schizophrenia. Dopamine is a key neurotransmitter there, and these patients have abnormal thoughts. But with Parkinson's disease, at least you understood that frontal cortex was missing dopamine. And so the exciting thing we do in my lab is we can record from populations of neurons, an entire ensemble or orchestra of neurons while it's performing these computations, and then we can take away dopamine and see what happens. And we can see what happens to specific neurons that we've tagged with dopamine receptors. We can see how these neurons communicate with these neurons. We can put these neurons in context. And the exciting thing is we can cross levels. So we can look at individual cells, we can look at populations of cells, and then we can look at macro level rhythms. And what we found is these dopamine neuron receptor expressing neurons are in phase with these rhythms that you can pick up at the scalp 4 times a second. And what that means is that if we understand how these neurons work, we can understand how to stimulate them. Let's say you want an orchestra to play Wagner or something. Pick your favorite composer, Radiohead, right? You can give them sheet music. You can stand up there and you can wave your arms and they'll go, right? But with Parkinson's patients, with that orchestra, you could stand at the front of the orchestra of these neurons and, it's not clear what to do. But with motor symptoms of Parkinson's, it's actually, you can stand in front of an orchestra, and let's say that was a motor cortex orchestra. You could stimulate it 15 times a second, 15 hertz, at the time when patients were stopping, and you could actually make patients go. So that's an incredibly beautiful description of how you can precisely intervene. And we actually understand the circuitry such that you can deliver targeted deep brain stimulation in the subthalamic nucleus or in the globus pallidus internal segment and cause Parkinson's patients who are stiff to move. But what if you could do that for thought? I mean,
Wow.
all of a sudden, if you could deliver deep brain stimulation targeted not at movements, but at cognitive symptoms, you might be able to make differences not only for Parkinson's patients who have these thought disorders, but for all diseases, all brain diseases that have thought disorders. I mean, we're talking Alzheimer's dementia, ADHD, schizophrenia. So it's an incredibly, it could be a gusher in the sense of the way we think about our ways of interfacing with the brain. And so that's the kind of that's a hard problem, right? Our brain is 82 billion neurons.
Wow.
There's several million, maybe a couple billion in the frontal cortex. But right now we don't know anything about the principles by how they interact. But I think that by understanding these frequency relationships and these specific relationships of these dopamine receptor neurons to the larger ensemble, we might be able to make progress in how to boost this. And we've actually have a couple of studies, some in mice and a few in humans, that show that we can actually make progress in our limited cognitive paradigm. We study how rodents and animals guide their movements in time, because how you move in time is sort of the clock speed in the computer. Like if your clock is off, everything else is off. So we study that process, but we're interested in the bigger processes.
So how many years do you think it'll take before the management of the cognitive and movement disorders related to Parkinson's looks different than it does now in clinical practice with our patients?
So that's a huge question. So one thing, and this is where the MD PhD really makes a huge difference, is figuring out how to get what your bizarre, kind of one-off observation of 2 mice can make it to a human being. So we really have to think about, so the key is that, the key in that making that translation is rigor and reproducibility. So I can tell you that there's a study in ALS where they had like 9 mice and they gave it minocycline, and they showed that there was a signal. And minocycline, the next step was clinical trials. We need to make sure that we can test something over and over again, a variety of different ways in a variety of different paradigms before we make it to humans. Because the danger is that we come up with something and we go to humans too quickly, and then you expose patients to the risks without any benefits. So if you look about human motor brain stimulation, there's actually a guide. So 1992, so in the 80s, basic science studies mapping the circuits, like what we're doing right now, was when they mapped the motor circuits. 1992, I think, was the first brain stimulation study. Before that, there was lesion studies that kind of predicted the brain stimulation studies. In the 2000s, where when we started to do human brain stimulation trials. 2010, I think, was the last big brain stimulation trial that showed it worked. So we're looking at 20 years, which, if you think about it, it seems like a long time. It seems like a lifetime. A lot of my Parkinson's patients are frustrated that they won't ever see the benefits. But the flip side, from the safety side, we are in an age where we can be guided by data. And so the ability to do that enables us to maximize the benefits while minimizing the risks. And I think that's absolutely critical for any research effort. So, what I referred to with 2 mice, we might start with 2 mice, but if we have a hypothesis, we're going to test it over and over again and try to falsify it, try to prove ourselves wrong. And it'd be interesting to know when something works and when something doesn't work, because that way you can guide human trials. But that being said, what could be, for me at least, what could be more exciting and what could be more meaningful than coming up with these, metrics? We're going to have a lot more patients with Alzheimer's disease and a lot more patients with Parkinson's disease in the coming years and decades. So, starting that research now will enable us to, move the needle, not only for one generation, but for every generation to come, because, where those generations start from is from, where we kind of leave off, right? So, we might be able to make a small difference today, but guess what? That'll be a bigger difference tomorrow, and that'll be an even bigger difference. Think about the development of diabetes drugs. We started with one drug, and now we have many, many drugs. We're able to move the needle. And in neurology, MS has made a huge advance from the first immunomodulatory therapy to now MS is a disease that we work really hard to manage. Even Parkinson's disease, started with levodopa, dopamine drug, dopamine precursor in the in the 70s, And now we have many, many types of dopaminergic drugs. But certainly there's a lot of this is a growth industry. The brain's a complicated problem, so we're not going to run out of talent.
Patience is a virtue. So,
Yeah.
Coach Kumar, we have a variety of different students watching this video today who are of all different ages. So, I'm going to ask you for some advice for the team members watching here. What's the advice that you would give to, let's say, your 12-year-old self or a 12-year-old student watching? And is that advice different or the same than, let's say, to someone who's in college right now who's interested in a STEM career?
So that's a great question, and the key thing I think is to, and this is a little bit, you've heard this before, but you might have heard it as find your passion, but I might say follow your passion, because once you've found something that you're very, very passionate about and that can make a difference both in your own way of thinking about things and you're excited about, it's hard to you know once you've found something you're excited about, if you follow it with as much energy and enthusiasm, I mean, only good things will happen. Mm-hmm. And when you're 12, it's easy to be passionate about other things. If you think about it, the way your passions sort of get pruned is you think you can't succeed. And so that's what I might say is the key thing, is that the key about following your passion is perseverance. It's not the ability to find passion. I often hear about people, well, I don't know, I'm not passionate about anything. Well, it's not that you're not passionate about things, it's just that you can't succeed at anything. So, and I might say that I'm not saying that everyone's going to succeed at everything, but the predictor of success is actually not smarts, it's not intelligence, background. The only thing that predicts success in my book is perseverance. Mm-hmm. So if you have a passion, if you persevere, you might not get to that end goal that you had necessarily, but you're going to have an amazing journey. So think about it. You might have a passion of climbing Mount Everest, say, right? So you try to climb Mount Everest, and in Mount Everest, it's hard. A lot of people die. Wouldn't recommend it for everybody. I'm personally, as a hobbyist mountaineer, I enjoy climbing. But even if I don't make it to my tall mountains, right? I am in the White Mountains, very good. Right on cue, right? So I love climbing mountains, but every mountain you climb, even the low mountains, the White Mountains I think that's Mount Lafayette, the view is phenomenal and the journey is exciting. So for me, like, if my passion is to cure XYZ or make a difference, I've gotten to do all these cool things scientifically, and I've gotten to do all these cool things medically, and been a part of these cool journeys, and that's the most important part. But I'm not gonna, climbing a mountain, doing science, doing medicine, it's a slog, and there are times of huge protracted slogs. And so you have to, people tell you no, or if people tell you that's not going to work, it might be possible that it's not going to work, and it might be possible that way is not going to work. But it's your perseverance to find a different way, find a different challenge, find a different path. And so that's I think the key thing that's going to persist. Now, the person at 12, you don't need to hear about passion, or necessarily. You do need to hear that if you persevere, you'll get there. I think when you're in college, there are a lot of people telling you that you need to do X to get to Y, or let's say getting into medical school, right? You need to take this class and do this. But I actually think the most important thing is to listen to your passion, because I think people can tell when you're doing something that you don't want to be doing, right? If you're doing something you're not excited about, it's obvious to everybody. On the flip side of things, if you're doing something you're super excited about, then you're going to do it the best you can. And so that's the key about success, I think, is to do things just the very best you can. And frankly, you can't do anything better than that. So just try your best, try your hardest, and listen to feedback, and adapt and persevere.
Awesome. Well, Kumar, we're going to wrap this up. I'm a huge fan of being on Team Kumar, and thank you for coaching us through this process here. And for those of you watching, please check out Dr. Naryanin's URL going over his lab and all the exciting work that he's doing. And you can also check him out on Twitter, send him a little tweet. But we appreciate your time, and stay tuned for future STEMinar events and future STEM events as well. Stay safe out there and stay healthy.
Thank you. Thank you very much.